Okay, if you see here, this is a basic diagram of nuclear reactor. Okay, a nuclear reactor will have uranium 235 embedded on the surface, uranium 238. Uranium 235 will go through a nuclear fission, right? So it will split to form barium and krypton to produce huge amount of heat energy, all right? That heat energy will be transferred to the coolant, which is called heavy water. This is called heavy water, all right? It's called heavy water. This is the heavy water here, okay? Heavy water is here, this one, okay, now, then what happened here? The heavy water here, the coolant here will become extremely hot. All right. It will flow through a water system, release the heat to the water system, and then come back as a cold coolant, go back to the reactor and absorb the heat out, go back to the water system, release the heat. So this is the circulation. Okay, next. After that, what happened? The heat from the hot cooler will heat up the water will start to boil. The steam will rotate the turbine generator to produce this huge amount of heat energy. Okay, go back to the reactor now. Okay. Inside this system, there will be graphite moderator, carbon, right? When the reaction started, the graphite moderator, once they lower it, what will happen is that it can absorb the high-speed neutron. See, neutron will come and split the nucleus of uranium-235. So this high-speed neutron, okay, right, will gain energy. It's a chain reaction. I'll show you in a while, okay? So the energy of the neutron increase, its velocity increases, and the whole thing will become faster and faster, and higher amount of energy will be produced. So to control the rate of reaction, they will lower the graphite moderator from time to time, which will lower the speed of neutron to control the reaction. Let's say huge amount of energy is produced and they need to stop the reaction. They will lower the control rods, okay? Control rods are made of cadmium, okay, and boron. So these rods, once they lower, it will absorb, okay, it will absorb the neutrons. So neutrons are absorbed, the reaction is stopped. And this whole system will have a huge concrete wall because the concrete wall will prevent any form of leakage. Shield, it's called a shielding, shielding system, shield. It will prevent any form of leakage. All right, so leakage is prevented. Clear? All right, so the leakage of radiation will not come out. Clear? And then if you follow the whole idea here, basically these reactors will be underground, okay? And then I told you huge amount of steam will be produced. The steam will rotate the turbine to produce electricity, but 30%, 40% or less than that will be used to rotate generators. The rest all actually sent out to the cooling towers, right? A chimney is used. So this is how they actually run the whole nuclear reactor, right? So basically, there's very minimum possibility for leakage of radiation. All are controlled under the concrete wall. This concrete wall can be 1 to 2 meter concrete wall thickness, and inside the concrete wall, they'll have very thick layers of plumbum. There's a lot of plumbum left inside it. Inside this wall, there'll be plumbum, all right? And so all this will prevent gamma radiation from coming out. The shielding is so strong, gamma cannot come out. Based on our syllabus, we use uranium-235 as the fuel rod, all right? It will start a chain reaction. Then we have control rod boron, okay, and cadmium to absorb neutrons to stop the whole reaction. Moderator graphite to slow down the speed of neutrons. Cooling liquid, the coolant is made of heavy water, we call it, with a very high specific heat capacity, able to absorb high amount of heat out of the reactor, right? And then thermal heat changer, the whole idea from the coolant to the water, and then to produce steam, right? This is the whole idea. And the thick wall, the shielding system. Okay, so the whole thing is done now. Okay, next. Okay, see, compare nuclear fission. Okay, what is fission? Splitting a heavy nucleus into a lighter nucleus. This is fission. What is nuclear fusion? Combining two lighter nucleus to form a heavy one, like hydrogen 2 and hydrogen 3. When they fuse, we get helium, right? Then fission or fusion, if you see carefully, both also are, if you see carefully, right? You see, it's a reduction in mass both, right? Both also release energy, and we calculate by using E equals to mc squared. So what is meant by nuclear fusion? Fusion there, combining several light nucleuses to form a heavy one. And then, see, a solution of phosphorus 32 with half-life 14 days watered onto soil plants by a farmer. The leaf is removed from the plant a few days later and tested for radioactivity. What is the purpose of doing the test? To identify the effectiveness of the fertilizer. All right. So if the radiation coming out a lot, it shows the plant was able to absorb the fertilizer properly. So the formula was a good one. If the radiation from the leaf is less, that means the plant was not able to absorb the fertilizer. So the formula developed was not a good one. Because phosphorus 32, once it is absorbed by plants, it starts to radiate because it got certain half-life, right? The radiation can be detected. So this is how they do it. Why phosphorus 32 is used? It will emit beta particles, all right, and can move through the body of the plant scan. Okay. Suggest an apparatus which could be used to measure Geiger-Müller tube. All right, next. Nuclear energy from controlled nuclear fission can be used to generate electricity. However, it is potentially dangerous at the same time. As the researcher, you are assigned to design a nuclear power station for the production of electricity. You take the following aspects into consideration while designing the power station. Structure and location. Structure, like what we discussed just now, must have a big shielding system, concrete wall, underground, far away from highly populated people, with a huge amount of water resource. Huge river or beside the sea, because you need a huge amount of water to cool down the coolant system. All right. Okay. Structure and location. How to protect the workers must be given the photographic film, or now it's more digital system. Workers must be given a proper suit to wear, and every area of the nuclear power plant must have detection system, right? And rescue system must be good, right? The workers must be scanned or screened on a regular basis to identify they are healthy or not, right? All these are done, right? Then the treatment of nuclear waste, what can we do, right? Based on the level of dosage, it must be treated. So, for example, placed in a barrel of plumber and go and plant it underground as deep as 20-30 meter and disclose the area. Don't let public know. No, you don't spend money to send to space yet. A lot of money. Maybe some countries doing, I don't think so. Okay. Next, uranium-238 decays by emitting a particle to form daughter thorium-234. Name the particle emitted. You see, 238 becoming 234. So it must be alpha. Alpha. Write down the equation. Okay, D2, write down the equation. So if uranium-238 decay based on the nuclear number 238 drop to 234. So nuclear number decreased by 4. Here. All right. So the idea here, alpha was emitted. So when an element release alpha, nuclear number drop by 4, proton number, 0, drop by 2. Proton number drop by 2, right? 92 become 90, 23 become 234, and energy is released. Okay, next. Sketch a graph of count rate against time. So this activity, count rate against time, to describe how radioactive materials decay, show how the half-life can be determined. So you look at it here, every time, whatever count you have, let's say 8,000 count per minute, for example, per minute, all right, it will drop to 4,000 count, and now drop to 2,000 count and drop to 1,000 count. So it will drop exactly half after its half-life time, another half after another half after that. So we will get a perfect curve. It's always curve, right? It will be always a curve. The curve will go down and go down. Okay. So this is how we are able to get the graph. Okay. So this is how we are able to know. And always remember, half-life shows that activity will decrease by half from the initial amount. If percentage, from the initial amount percent will drop by half. If fraction, will drop by half. If count rate, will drop by half. Mass also, say example 80 gram, drop to 40 gram. Example, initial amount is 4,000 count per minute. After the first half-life, become 2,000 count. Okay. Based on this question, half-life is 15 days. Calculate time taken for activity of the radioactive to decay to 12.5%, which is the remaining balance. All right. If remaining balance 12.5%, amount decay should be 87.5%. So follow the idea. 100% will drop to 50 from initial amount by half. 50 will drop to 25, and finally 25 will drop to 12.5. So it shows 3 half-lives taken a day. All right. So total time should be number of time half-life occurred times the time. All right. So 45 days. This is the way to answer this question. Okay, based on this question, what happened here? We need to identify the energy in EV. But before that, what we do? We will find the energy in the form of joules first. Okay. So once an equation is given, what we do? We identify total mass before the reaction in the unit of atomic mass. All right, ULA. Okay. So we take this plus this. Before uranium plus 1 single neutron, you get this. Then we take the total mass after the reaction, which will be 1 krypton, 1 barrier, and 3 of these neutrons. All right. So we get this. If you find the total mass of krypton, barium, and 3 of these neutrons, we'll get this here. Okay, next. Now, how to find defect mass? Defect mass will be total mass of this minus total mass of this. So this minus this get defect mass. Total mass of this minus this get defect mass. This minus this get defect mass. Defect mass will be this. Clear? So we get this now. So take this value, change it to kg. How to change to kg? So take this atomic mass unit, all right, in AMU unit, okay. We change it to kg. So take the value times this. Always remember, every 1 atomic mass unit is equal to this amount in kg, okay. So take this value times this, we get in kg. Now you get the defect mass in the kg value or unit. Now you are able to identify the energy produced due to the changes of mass to energy. Use this formula equals mc square. Substitute this value m here, and c is always equals to speed of light. Okay, so you'll get this amount of energy produced by this one single uranium split to krypton barium. The question also wanted to find the answer in EV. So what we do, we know that every 1 times 10 to the power of minus 13 joules equals to 1 mega EV. So 1 joule will be 1 divided by this. So we get this amount of joule times lah. With this, get this. But the answer one in EV, right? So final answer will be 2.8524942 times 10 to the power of 8 EV, because this mega is times 6. All right, this is how to solve this question. Okay, based on question 5, we need to find the amount of energy produced by using this formula. All right, so we need to find total mass before the nuclear fusion. This is a fusion, guys. So before fusion, these two, right? Mass of hydrogen 2, hydrogen 3, we get this. And total mass after is the mass of helium and 1 single neutron, we get this. So the defect mass should be total mass before minus after. All right? Before minus after. So this minus this, we get this. This is the defect mass in the unit of atomic mass unit. Now, earlier we saw whenever we get the unit in atomic mass unit, we have to change it to kg. So we change this to kg mass times. This will be given, okay? 1.66 divided by minus 27, you get this. This is the value of the defect mass in kg. Take this times the speed of light, you'll get the answer in joules. So we are able to get the answer in joules, all right? So this is what's happening in the core of the sun.